All right, we're going to dive into an idea that honestly sounds like it's straight out of a science fiction movie, but it's actually the bedrock of our reality. I'm talking about Albert Einstein's special theory of relativity. And don't worry, you can forget about all the heavy math. We're going to break down how just two simple rules completely changed everything we thought we knew about the universe. How they can stretch time, shrink space, and even reveal the incredible energy that's locked inside every single atom. So let's just start with the one really bizarre idea that flips everything on its head. Just ask yourself this. What if the speed of light isn't like anything else? What if it's the universe's one and only unbreakable speed limit? I mean, no matter how fast you're moving towards it or how fast you're running away from it, you will always measure its speed as the exact same number. It makes no sense, it goes against all our intuition, but if you can just hold on to that one strange fact, well, that's the key that unlocks all of relativity. Now, to really get why this was such a bombshell, we've got to rewind the clock a bit, back to the late 1800s. Physics was in a bit of a crisis. You see, the whole field was built on these two magnificent foundational pillars. And the problem was, they completely contradicted each other. Something was about to break. So on one side, you had the giant Isaac Newton. His laws of motion had been king for centuries. And they made perfect sense, right? If you're on a train going 50 miles per hour and you throw a ball forward at 10, somebody on the ground sees that ball moving at 60. Speeds just add up. It's common sense. But then, on the other side, you had James Clerk Maxwell, and his brilliant equations for electricity and magnetism predicted something, well, something totally bizarre. They said the speed of light is a universal constant. It doesn't matter if the flashlight is standing still or strapped to a rocket ship. The light from it is always moving at the exact same speed. So, which one is it? You see the problem? Physics was at a total standoff. So what do? Do you abandon Newton, the guy whose work was the foundation of mechanics for hundreds of years? Or do you say Maxwell's theory, this incredibly successful theory of light, has to be wrong somehow? This was the epic puzzle that a young, unknown patent clerk named Albert Einstein was about to solve. And Einstein's solution, it was just an act of pure genius. See, he didn't try to pick a side or prove one of them wrong. Instead, he asked this really radical question. What if? What if they are both right? He decided to just accept that. And from that wild starting point, he built a whole new way of looking at reality. And it was all based on just two simple rules. Okay, so here they are, Einstein's two golden rules. First up, the principle of relativity. This is actually pretty intuitive. It just says the laws of physics, like gravity making your coffee stay in its cup, work the same for everybody moving at a constant speed. There's no special spot in the universe that's at rest. It's all relative. But then there's the second rule, the real troublemaker. The speed of light is the same for everyone. Period. Always. And this is where the genius comes in. Einstein just decided, okay, I'm taking these two ideas as absolute gospel. Let's just follow the logic and see what happens, no matter how weird it gets. Because this is where things get, well, weird. The moment you accept those two simple rules as true, reality itself starts to come apart at the seams. Our most basic, fundamental ideas about space and time, they start to bend and stretch and just behave in ways that make absolutely no common sense. So what kind of a crazy universe are we living in if those two rules are true? How does it all work? To figure that out, we're going to use one of Einstein's favorite tools, a thought experiment. Okay, picture the simplest possible clock you can imagine. It's not gears and springs, it's just a single particle of light, a photon, bouncing back and forth between two mirrors. Every time it makes a round trip up and down, that's one tick of our clock. It's a perfect, flawless timekeeper. Now, if you're the one holding this clock, it's super straightforward, right? From your point of view, the little particle of light just travels a short, straight line up, hits the mirror, and travels a short, straight line down. Tick, tock, simple. But now, let's say that same clock goes flying past you at an incredible speed. From where you're standing, you see the photon still has to get from the bottom mirror to the top one. But because the whole clock is moving sideways, the light doesn't go straight up and down anymore. No, from your perspective, it has to travel a longer, diagonal path to catch up to the top mirror. And right here, this is the mind-bending moment. Remember rule number 2, the speed of light cannot change. It's the universal speed limit. So, from your point of view, that little photon has to travel a longer distance, but it's not allowed to speed up to get there. There is only one possible way for that to work. The tick itself must take longer to happen. This incredible effect has a name. It's called time dilation. And I want to be really clear, this isn't some kind of optical illusion. For you, the stationary observer, time for that moving clock is literally, actually, physically passing more slowly. It's a fundamental property of our universe. The faster you move through space, the slower you move through time.
But wait, it gets even weirder. You see, you can't just go messing around with time and expect space to be okay with it. They're connected. They're two sides of the same coin we call space-time. So, to keep the speed of light constant for everyone, if moving clocks have to run slow, then moving rulers have to get shorter. It's called length contraction. An object moving at a really high speed physically shrinks in its direction of motion, at least from the perspective of someone standing still.
And believe it or not, Einstein wasn't done blowing our minds. By following this exact same thread of logic, he stumbled upon a hidden connection between two things that everyone thought were totally separate: mass and energy. This led to probably the most famous equation in all of history. He put it in his very technical way in one of his papers back in 1905. But basically, what he was saying is that when an object gives off energy, say as light or heat, it must also be losing a tiny, tiny amount of mass. It was the first time anyone had ever suggested that mass and energy weren't separate things, but were actually interchangeable. Now think about what that really means. Mass isn't just stuff. It's not just dead weight. It is actually an incredibly dense, concentrated form of potential energy. Every single physical object, you, me, this entire planet, is a massive reservoir of energy just locked up inside its mass. And that brings us to the iconic equation, E equals mc squared. Energy equals mass times the speed of light squared. Now, the c part, the speed of light, is already a gigantic number, but the c times squared part, that's the real kicker. When you square that number, it becomes astronomically huge, and that's the secret. That's why converting even a tiny, minuscule amount of mass can unleash a truly colossal, almost unimaginable amount of energy. Okay, I know what you might be thinking. This is all really fascinating, but it's just weird thought experiments and abstract physics, right? Wrong. The effects of special relativity aren't just confined to a chalkboard. They are the invisible engine running behind a lot of the modern technology that we use every single day. I mean, look at this. The GPS in your phone or your car only works because the satellites are constantly correcting for time dilation. See, those satellites are moving really fast, so their clocks literally tick slower than ours down here on Earth. If the system didn't account for that, your GPS location would be off by several kilometers every single day. Or take particle accelerators, like at CERN. When they smash atoms together, they have to calculate for the fact that a particle's mass actually increases as it gets closer to the speed of light. That's E equals mc squared in action. And of course, every nuclear power plant is just a machine for converting a tiny amount of mass into a huge amount of energy. This isn't theory, this is real-world engineering. So what Einstein did was just incredible. He showed us that the very things we thought were the most constant, the most reliable things in the universe, the steady tick-tock of a clock, the fixed length of a ruler, are not constant at all. They're flexible, they're relative, and they depend on how you're moving. And that really leaves us with this one profound, final question to think about. If space and time themselves can bend and stretch, what's left in the universe that we can actually say is truly absolute?